demonstration works for you, but not so much for me. Do you hear the pitch going up and down? There you go, yeah. Okay. And is it possible that when the thing is going toward you, that maybe it's a higher pitch, and when it's going away from you, it's a lower pitch? I don't know if you can tell that. Sometimes you hear a reflection, so it's very hard to tell, right? I don't really hear this because I'm right there. You know, actually, I hear a little bit of shift from ear to ear because it's approaching or receding from my ears. So the key concept here is that the frequency is changing that we hear in the air because it's either approaching us or receding from us, right? This is called moving source Doppler effect. Okay. Now to demonstrate moving observer Doppler effect, okay, I'm going to do this. Did you hear that? And of course you didn't really hear it because you weren't running by it, but I heard it. As I approached, I heard a little bit higher, and as I went away, I heard a little bit lower. Okay, I'm going to turn this off because I can't actually talk while it's going on. Okay, so if you've ridden a train, has anybody ridden a train? And you approach, and as you go through towns, you hear ding, 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 little crossing bells. Yes, ding, 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 ding. And as you approach them, you hear ding, 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 ding. As you go by, you hear ding, 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 ding. Did you remember this? Yeah. So that is moving observer. There's two types of Doppler shift. Okay, and there are two different formulas for it. Right, so there's moving source, moving observer, right, and then there's moving observer, right, and we're going to do both of these because that's what kind of people we are, right. But for both of these guys, the key concept is that if you are approaching, right? If either you're approaching the source of the sound or the source is approaching you, if you're getting closer, right, then it's a higher pitch, higher frequency. And if it's receding, then it's a lower frequency. Can we all remember that? Is that something we're going to remember? Are we going to remember that? Yeah, this is a simple, because the problem is that the formula gives you, it's like a plus or minus, and one is for approaching, one's for receding. But you need to, this is the thing that you need to remember. Okay? Now, for moving source, okay, for a moving source, the wavelength itself is actually shortened by the source. Because the source moves to the side, the wavelength is actually shortened, right? And so if it's lambda, if that's the wavelength that it would be if it was sitting still, right? Lambda prime is the shifted one, the shorter wavelength. And let's derive this for the wavelength in front, right? So this guy is equal to the unshifted wavelength if you're sitting still, right? Minus the velocity of the source times the period. This is the simplest way to do it, right? So you've got these waves, right? You've got a wave here, right, and you've got a wave here, right? This guy has been shortened by some amount. This is what the wavelength would be, right? That's what the wavelength would be, but that's this distance, right? But in fact, it's been shortened by some amount. This is our shifted wavelength, right? It's been shortened by some amount, and that amount that it's been shortened is the speed of the source. So that's our source, right, times the time in between the waves. Does that make sense? Yeah? We've just shortened it because during that time between one wave and the next, we've moved some distance, right? And then, of course, we need a formula for frequency, right? And so to make frequency, I think what we do is we divide, we go V over lambda prime. That's going to be our shifted frequency, right? Okay, so that's going to be V divided by lambda minus. I'm just deriving a formula. I know what the end formula should be, so I'm just headed that way. Okay. Okay. I think the next thing to do is to multiply the top by the unshifted frequency and multiply the bottom by 1 over the period. The actual period, the actual frequency. Now, aren't those the same thing? Can't I do that? Isn't the frequency equal to 1 over the period? So why do I put the frequency on the top, but 1 over the period on the bottom? Why do I do that? Is that to cancel something? Because I know the answer? Yes, I already know the answer. I worked this out before this class. I can never remember this derivation, but this I think is the slickest way I've derived it ever. Okay? So I worked this all out. I think this is going to work just like a charm. Okay? And now this is going to be our shifted frequency is the original frequency, okay, times the velocity. And then in the denominator, we get 1 over the period, so we get lambda over the period. Bless you. And we have some cancelage, don't we? Yeah, that cancels out this guy, doesn't it? And then what is the wavelength over the period? No. The waves are all 10 meters long, and it takes a half a second for them to go by. 20 meters per second. The rate, it's the velocity, the wave speed, isn't it? In this case, it's the speed of sound. Okay? So this V here, isn't this guy just V? Don't you love it when people do that? Like, damn it, now I need to do the whole thing over again. Yeah, there it is. Right? So this is our frequency, this is our formula for moving source. Okay? For moving source, it's that the shifted frequency is the original frequency times the speed of sound divided by the speed of sound plus or minus. In this case, it was minus, right? But I'm going to say plus or minus. There we go. And then everybody wants to make this S be like for sound. But no, this guy is the speed of sound, right? This is your speed of sound. And if they don't tell you what to use 343 meters per second. I'll put a question mark, right? Okay. Same thing for this guy, right? Okay. And then this is the source velocity. Why is it plus or minus? Yeah, one's approaching, one's receding. Now, which one's which? Well, we figured it out for approaching, didn't we? Because we made the short wavelength, did we? We subtracted. So minus must be for approach. Plus must there be receding, yeah? Okay. Is that right? Yeah. Now, who among us is going to remember that? Because it's not in the data packet. The other formula looks similar to this, only it's the other way around. Are you going to remember that? Are you going to? Or are you possibly going to remember this? Isn't it, don't we all, we knew this before this class. You know that race cars sound like this. Don't you? They never sound, right? They never ever do that, right? Right? Isn't that correct? Yeah, they never do that. So you know that when it's getting closer, it's a higher frequency. When it's going away, it's a lower frequency, correct? So even if you looked at this formula and you didn't know that making the denominator smaller would make the numerator bigger, and therefore it would be a bigger velocity, bigger frequency, so it would be approaching, right? You would just, if you didn't know what to do, wouldn't you do both? One would give you a higher frequency, one would give you a lower frequency. And if you knew it was approaching, you'd use the higher answer. And if you knew it was receding, you'd use the lower, wouldn't you? Yeah? It's really not that hard. But kids will just sit there and go, I don't know which one to use. We'll use both. Use them both, figure it out afterwards. If you can't figure out, looking at it with math, which thing to use, the plus or the minus, then do that, right? But I'm pretty sure right now the minus is approach, right? Plus in this case is recede. Somebody has a question. No, yes. Okay. So now we need moving observer, which is a different formula. So here's our first formula. Okay. Kind of carve off that a little bit. And now we need moving observer. Okay. And moving observer is a different thing. With moving observer, moving source. Look how fast you are learning. Okay. With moving observer, the waves themselves in the air are not changed in length. You're not creating actually different waves in the air. It's just that the observer, look at this thing, look. There it goes, chunking along. Can't animate like text. Right? Okay. It goes, the observer goes through it, and as they approach, you have to imagine that these sound waves are going out. Yes? Okay. As they approach the sound waves, don't you see them faster? Yeah? And then as they're coming at you from behind, they go by you slower. Because in this case, your velocity is added, you're approaching, and it's the sum of the velocities, the speed of sound plus your velocity that you're seeing them. And then as you go away, it's the